So, you've written some Kotlin, but have you ever wondered how that code actually talks to the silicon at the heart of the device? The answer lies in a rigid 5-layer architecture that every platform engineer must know inside and out. This structure, as you can see highlighted, is the absolute foundation of AOSP. It dictates how everything from a simple button press to a complex video render is handled by the system. Let's start at the very bottom and work our way up. Every Android device, no matter the manufacturer, has a secret identity. It's a Linux machine. At the very bottom of the stack sits a modified Linux kernel, the absolute bedrock of the entire system. Most people trip over this because they assume it's a standard desktop kernel. It is not. It's heavily customized for mobile, focusing on things like aggressive power management and unique drivers. This kernel is the ultimate gatekeeper to the hardware, and without it, nothing else can run. How does your app's request to take a photo actually fire the camera flash? That translation happens here in the kernel's hardware drivers. These are highly specific pieces of C code, often written by the chipset vendors like Qualcomm, that know the exact memory addresses and commands to control the physical hardware. You can find the source for these in the kernel tree. For example, the camera driver might live under drivers/media/platform. Now, controlling the hardware is one thing, but managing its resources is another. With hundreds of apps wanting RAM, why doesn't your phone just grind to a halt? You can thank the kernel's memory management and a very important Android-specific component, the Low Memory Killer Daemon or LMKD. Here is what actually happens under the hood. When memory gets tight, LMKD doesn't just randomly kill processes. It uses a hierarchy of ohm score adjust values to decide which app is least important, usually the one you haven't used in a while, and terminates it to reclaim memory. You can see this happen in real time by watching logcat for kill messages from LMKD. Now that your apps have memory, how do they get a slice of the CPU's attention? That's the job of the kernel's process scheduler. It's a relentless traffic cop, switching between thousands of threads hundreds of times per second to create the illusion that everything is running simultaneously. The trick that took me years to figure out is that Android's scheduler is tuned differently from a desktop. It heavily prioritizes the foreground app's UI thread to ensure a smooth, jank-free experience above all else. This focus on responsiveness has a profound impact on security. Every single app on your phone is a prisoner, locked in its own sandbox by the kernel's security model. This is built on standard Linux user IDs. Each app is assigned its own UID when installed, so the kernel can enforce rules about which files it can access. On top of that, Android adds SE Linux, which provides mandatory access control. This means even if an app is running as root, SE Linux policies can prevent it from touching critical system files, a defense-in-depth strategy that's crucial for device security. Why can your phone last all day on a tiny battery? The secret is the kernel's aggressive power management. It's constantly trying to put the CPU into a deep sleep state to save power. When your app needs to do background work, it must acquire a wake lock through the Power Manager Framework API. This is a direct message to the kernel saying, "Do not sleep yet, I am doing something important." Misusing wake locks is the number one cause of battery drain, a lesson many developers learn the hard way. So if you look at the highlighted line here, it says the kernel acts as an abstraction layer. This is the key concept. The layers above the kernel, like the Android framework, should never need to know if they are running on a Qualcomm or a Samsung chip. The kernel and its drivers provide a standardized set of features like open camera or write to flash storage, hiding the messy hardware-specific details. You can even see which specific kernel your device is running with a simple command. You don't have to guess what kernel you're running. You can ask the device directly. If you open an ADB shell and type the command you see on screen, uname -a, the system will print the exact kernel version, build date and architecture. This is often the very first thing a platform engineer does when debugging a weird low-level hardware issue. It tells you exactly which kernel source code you need to be looking at. But the kernel doesn't work alone. It has a partner. The kernel provides a raw interface to the hardware. But how does the high-level Android framework talk to it in a standard way? That's the entire purpose of the hardware abstraction layer, or HAL, which sits directly on top of the kernel. Most people trip over this because they think the framework calls kernel drivers directly. It doesn't. The HAL is the critical middleman, and its existence is the reason a single Android OS build can run on thousands of different devices. So why does the HAL even exist? Look at the highlighted text. Every hardware maker has their own secret sauce, their own proprietary drivers for their specific silicon. Google can't put all that proprietary code into AOSP. The HAL creates a contract. Google defines a standard interface like iVibrator.aidl, and the hardware vendor like Qualcomm implements that interface using their own private proprietary driver code. This allows the OS to be open source while the drivers remain closed. Here's what actually happens under the hood when your code calls vibrator.vibrate. The Java framework code doesn't know anything about the vibration motor. It makes a binder call to the HAL module for the vibrator. That HAL module, which is a shared library loaded by the system, then translates that generic vibrate command into the specific proprietary instructions needed by the kernel driver for that particular device's hardware. This standardization is what makes Android scalable. In the old days, a bad HAL implementation could crash the entire system. That changed with Project Treble. As you can see highlighted, modern HALs run in their own sandboxed processes. They communicate with the framework using a very stable, well-defined IPC mechanism called AIDL or HIDL. This means the Android framework can be updated independently of the vendor's low-level code, which is the entire basis for how seamless OTA updates work today. Let's look at what one of those definitions looks like. This code block on screen is a perfect example of a modern HAL interface defined in AIDL. Notice how simple it is. It defines an iVibrator with two methods, on and off. This is the entire contract. The Android framework only knows about these two methods. The vendor's job is to provide a C++ or Rust implementation of this interface that does the actual work. This clean separation is one of the most important architectural achievements in modern Android. Sitting above the HAL is a massive layer of native code that provides the core plumbing for the entire system. This isn't Java or Kotlin, it's high-performance C and C++ code that handles everything from graphics rendering to the very runtime that executes your app code. You can think of this layer as the engine room of Android. It's where the heavy lifting happens, providing the foundational libraries that the Java framework will eventually wrap. Why isn't all of Android written in Java or Kotlin? The answer is performance. For certain tasks like rendering graphics or decoding video, you need to be as close to the metal as possible. That's why, as the text here shows, core components like the graphics compositor and media frameworks are written in native C++. These libraries are the workhorses of the system, optimized for speed and efficiency on embedded devices. Every C program needs a standard C library, a libc, for basic functions. Android doesn't use the standard GNU libc you find on desktop Linux. Instead, we built our own, called Bionic. The trick here is that Bionic was designed from the ground up to be lightweight and fast, specifically for the memory and power constraints of mobile devices. It's also responsible for the low-level implementation of the binder driver interface, making it the foundation of all IPC in Android. How do all the different app windows, the status bar, and the wallpaper get combined into the final image you see on screen? That's the job of a single critical native process called Surface Flinger. It takes all the graphics buffers, or surfaces, from every visible application and composes them into a single frame, which it then sends to the display HAL. If you ever run adb shell dumps surface flinger, you can see a live list of every single layer on the screen at that moment. When your app plays a video, it's not actually decoding the H.264 stream itself. It's using the media framework, historically known as stage fright. This is a set of native libraries that uses hardware-accelerated codecs to handle audio and video playback and recording efficiently. By centralizing this in a native framework, we ensure that all apps get performant media handling without having to bundle their own, often buggy decoders. Almost every app needs to store structured data, and the default choice on Android is SQLite. This isn't just a library we decided to include, it's deeply integrated into the platform. The Content Provider API, which is a core part of the Java framework for sharing data between apps, is fundamentally built on top of SQLite's database engine. It's a powerful file-based SQL database that runs directly inside your application's process.
For games and other graphically intensive apps, you need direct access to the GPU. Android provides this through standard native APIs like OpenGL ES and the more modern, lower overhead Vulkan. These are not Android-specific inventions. They are cross-platform industry standards for 2D and 3D graphics rendering. The Android framework simply provides the hooks for an application's native code to get a drawing surface and then use these APIs to render directly to it with maximum performance. So we have all these powerful native libraries, but how does your Java and Kotlin code actually run? That's the job of the Android runtime, or ART. Since Android 5.0, ART replaced the old Dalvik VM. Most people think of it as just an interpreter, but that's not the full story. ART is a sophisticated managed runtime responsible for compiling, executing, and garbage collecting your app's code. When you build your app in Android Studio, your Java and Kotlin code is first compiled into standard Java bytecode, and then it's converted into a format called Dalvik executable or DEX bytecode. This DEX format is what's actually packaged inside your APK. Here is what actually happens under the hood. When you install the app, ART takes these DEX files and performs ahead of time compilation to produce a native OAT file, which is what the CPU can execute directly. How does ART make your apps run fast? It uses a clever hybrid approach, as you can see highlighted. It performs ahead of time compilation when the app is installed. But while the app is running, it uses a just-in-time JIT compiler to re-optimize hot code paths. Even better, it uses profile-guided optimization, PGO, meaning it watches how you use the app and then recompiles it during device idle periods to be optimized for your specific usage patterns. Finally, we reach the layer where most app developers spend their time, the Java API framework. This is the magic layer that takes all the powerful, complex native components we just discussed, Surface Flinger, ART, the HALs, and exposes them as clean, easy-to-use Java and Kotlin APIs. When you call getServiceSystem context.activityService, you are reaching into this layer to get a handle to one of its core components. What is the Android framework really? It's not just a collection of utility classes. It's a set of long-running services, almost all of which live inside a single crucial process called system server. This process is started by Zygote at boot and runs for as long as the device is on. It hosts the essential managers that control everything about the system's behavior, and your app communicates with them constantly using Binder IPC. The most important of these services is the Activity Manager Service, or AMS. I personally spent years refactoring this code in Android 11 and 12. AMS is the ultimate authority on what your app is allowed to do and when. It decides when to start your activities, when to create your process, when to deliver broadcasts, and when to kill your app. Every single component lifecycle change goes through AMS, which you can find in framework/base/services/core/Java. While AMS manages the state of your app, the Window Manager Service, or WMS, manages its visuals.
WMS is responsible for handling the windows of all applications, deciding which one has focus, how they are ordered on screen, and managing screen transitions. It works hand in hand with Surface Flinger. WMS provides the policy and metadata about windows, and Surface Flinger does the actual low-level graphics composition based on those instructions.
How does the system know which apps are installed, what permissions they have, or if their signature is valid? That's the job of the Package Manager Service, or PMS. When you install an APK, it's PMS that parses the Android manifest.xml, assigns the app a user ID, and stores all of this metadata in tightly controlled files under /data/system. Every time your app starts, AMS has to query PMS to get the information it needs to run your code. If you want to become a platform engineer, this is where you live. As the highlighted text says, the vast majority of AOSP framework development happens within this layer. The trick that took me 3 years to figure out is that to solve any hard problem, you have to trace it through the layers. You start at the Java API, trace it into the framework service in framework/base, then down into its native C++ counterpart, and sometimes all the way down to the HAL. You can spy on these framework services at any time. The dumpsys command is the single most powerful tool for an AOSP developer. If you run adb shell dumpsys window as shown here, the window manager service will dump its entire internal state to your console. You can see every window, its position, its visibility, and who has focus. This is not an approximation, it's the literal ground truth from inside the system server process. Finally, at the very top of the stack, we have the applications themselves. This is the layer that users actually see and touch. It's important to understand that the system makes a huge distinction between two types of applications, those that ship with the device and those the user installs later. This distinction is not just about where they are installed, it's about trust and permissions. The apps that come pre-installed on your phone, the dialer, the settings app, the launcher, are called system apps. Here's the key. As you can see highlighted, these apps often have special privileges. They can be granted permissions that normal apps can't get, and they can call internal framework APIs marked with @hide. This allows them to perform system-level functions like changing network settings that are rightly forbidden for third-party apps. Every app you download from the Play Store is a third-party app, and the system treats it with extreme suspicion. It runs in a strict sandbox with a unique user ID, and as the text shows, it can only interact with the system through the public, well-documented Java API framework. It cannot access hidden APIs or gain special permissions. This strict isolation is the cornerstone of Android's application security model, protecting both the user and the system from malicious or buggy code.
Enjoyed the video? Hit like and subscribe for your regular dose of AOSP customization. Thanks for watching. See you in the next one.